Okay, so today we are going to start by plotting the Bode diagram for our open loop response in the system that we've been working with. So if you want any more information on what's on your screen right now and how we found all of this, please go check out the past videos in this playlist. They give a lot more detailed information. So we are going to start out by finding our Bode diagram. So we already know our GC, our GP, and our GM transfer functions, although we know that our GM transfer function is just 1. So we're just going to ignore our GM transfer function for this problem. So we also know that our GC and our GP transfer functions multiplied together. We already found this as our transfer function in the forward direction. So that's just what we're going to use in this problem. So we're going to start out with sig.bode of our transfer function in the forward direction. So we can see that this gives us 3 arrays of values. So our first array is our frequency values, or our omega in radians per second. Our second array is our amplitude ratio decibel values. And then our third array is our phase lag values in degrees. So we can set this equal to our omega, our decibel values, and our phase lag values. And now we can plot this out to our Bode diagram. So I'm going to come over here and grab my codes, or my plot starter. And now we are going to have 2 different plots. So our x value for both plots is going to be our omega. And then our y value for our first plot is going to be our decibel values. And the y value for our second plot is going to be our phase lag values. So we are going to set our rows equal to 2 and our columns equal to 1. And like I said, our x will be omega in both of our graphs, and then we're going to set our y equal to our decibels. We are going to assign this to our first row and our first column, and then we are going to name this our decibel graph. And then we want to do the same thing for our phase lag values. So we're going to now have our y equal to our phase values. Our row is equal to 2, and we are going to name this our phase graph. And typically in Bode diagrams, our x-axis is on a logarithmic scale, not a linear scale. So we have to update our code to have our x-axis in the logarithmic scale. So we can hit Shift-Enter. And now we can see both of our plots. So the first thing that we want to start looking at is our crossover frequency. So our crossover frequency, once you go under a negative 180 degrees on the phase graph, your system becomes unstable. So we're going to go to our phase graph, and we are going to find where our graph crosses negative 180. And it seems like that's at about 1.15 radians per second. So now we are going to go up to our decibel graph, and we are going to find the same value of our omega. So we can find that at 1.15 radians per second, which is our omega, our decibel graph is about at negative 6.5 decibels. So now we can start looking at finding a numerical value for our amplitude ratio. So if we want to find these at our omega is equal to 1, like we did in this last problem down here, our omega was equal to 1, we can do another sig.bode of our forward transfer function, and we can tell our code that we want the values at omega is equal to 1. So we can see that this outputs our first array as 1 because that's our omega array. Our second array is giving us our decibels, and we can see that that's at about negative 3.87. And then it gives us our phase lag at negative 178 degrees. So now using the root power quantities to describe decibels, we can find the actual numerical value for our amplitude ratio. So we can say that our amplitude ratio is equal to 10 to the power of dB divided by 20. And again, this is using our root power quantities to describe our decibels. That is a equation that someone figured out a long time ago. So if we want to see what our amplitude ratio value is at omega is equal to 1, we can just input our AR equation, and then if we click AR, we can see that this gives us about 0.64 for our amplitude ratio. And actually we can compare this down to our graph of our input and output. And if we zoom in here, we can see that the output of our system was also around 0.64. So if I give this more data points, I bet we can get closer to 0.64. So we can see that at the very top of our graph here that we found in the last video, our amplitude ratio is also 0.64, so that just kind of proves that you can use either of these ways to find the amplitude ratio. Okay, now there are a few key concepts that I would like to highlight. So we were already kind of talking about our crossover frequency, but I wanted to talk a little bit more about it. So our crossover frequency is where we find our phase diagram reaches 180 degrees, and then we go to our decibel diagram and find out, or from the omega value that we find at negative 180 degrees from our phase diagram, we then go to our decibel diagram and find that same omega and find our decibel value. If our decibel value is over 0, that means that our system is unstable. And if it's under 0, that means that our system is stable. So in our example, like I was talking about, we can see that we reach negative 180 at about 1.15. And if we find that on our decibel diagram, 1.15 is about negative 6.5 decibels. So this means that our system is stable at the moment. The other key concept that I wanted to mention was our phase margin. So to find the phase margin, you find where 0 is on the decibel plot, where our decibel value is equal to 0, and you find that radian per second value, or the omega value, and you take that omega value and find it on your phase plot, and then you take the difference between where that point is and where 180 degrees is. So you want your phase margin to be positive, since if we are under 180 degrees on the phase diagram, our system is going to be unstable, and if we are above 180, then our system is going to be stable. So here in our case, we can see that when our decibel is around 0, our omega value is about 0.8. And if we find our omega value at 0.8 on our phase graph, we can see that our value is around negative 170. So if you have negative 170 minus 180, so plus 180, we're going to have a phase margin of about 10 degrees. So this means that our system is about 10 degrees away from becoming unstable. So now we are going to rerun our Bode diagram with our Kc value, or our proportionality constant, equal to 3. We're going to see what this does to our, delete this, we don't need that anymore, and we don't need our ratio, and we don't want this set to omega equals 1 anymore, we want to see the whole graph. So now we can see that our crossover frequency, so when we reach negative 180, our omega value is about 1.15 still, but if we find 1.15 on our decibel graph, we can see that our decibel value is 3, which means that we are over 0, so our system is now considered unstable. And for our phase margin, we can also see that our decibel value is approximately 0 when our omega value is about 1.32. And if we find 1.32 we're about negative 182 degrees. So that means that we have a phase margin of about -2, which also shows that our system is unstable. So now I'm going to rerun our entire code with our new KC value. And if we go down to this plot that we were using in our last video, we can see that the oscillations begin small and then they increase and they keep increasing until they'll probably reach infinity. So they're never going to become stable in this system. So with all three of these things said, our system is unstable if we have a KC value of 3. Thanks for watching.